Hello everybody, we're getting ready to do 2.7 for Algebra 2 Math, and email me here if you have questions, if you need online tutoring, all this other stuff. 2.7, apply the fundamental theorem of algebra. We have a skill check at the end of part 1 here of 30 points for the skill sheet. And then there's 15 points of notes to take. If you need note-taking guides, contact me. Okay, teachers, here's your bell work here. Give your students 5 minutes to complete this, and they should attach an answer sheet to this because there's no way there's going to be enough room for this. So students, attach an answer sheet to this warm-up problem here. A pyramid has square root of base sides lengths x and a height of 2x minus 5 and a volume of 3. Write a polynomial equation to model the situation here. Length x, so we need to find x when we know the height here of 2x minus 5 and a volume of 3. So knowing your volume, figure out your sides and then your height. And then for a swimming pool to be set in the ground, width of the pool is this, and then depth is that, and more in depth. The pool holds that. What are the dimensions of the pool? Again, going from your volume back into your dimensions. Okay, welcome everybody back. Welcome back. Hopefully you got your solutions. This is number 1 here. We go from, here's our plug-in from our into our volume formula here. We go through our calculations there, and we come up with this cubic function here, and then we can figure our possible solutions by using our rational zero theorem here, and this is what we come up with: factors of this and factors of your coefficient. And then the swimming pool problem, we have to have a volume formula here, and then we do our plug-ins here. W is that, length is that, and then we know our volume, which is here, and then we just plug in and go through this, and we come up with a cubic formulation here. And then we do a possible zero here at 5. So we test D. We divide 5 into this manifestation here, and we get this here. So volume d minus 5d squared plus 45d plus 400. So again, we plug in 5 and we get these dimensions here: 10 feet wide, 40 feet long, and 5 feet deep. Okay. You found zeros using the rational zero theorem. You will classify zeros as polynomial functions, so you can the speed of a boat. So we have this equation here, which becomes this after you factor out an x minus 4 from that. When factored, it has only two distinct solutions, -3 and 4, because the factor x minus 4 appears twice. However, you cannot count the solution 4 twice, so would count it as a repeated solution. This third degree equation has 3 solutions: -3, 4, and 4. The previous result is generalized by the fundamental theorem of algebra, come up by Gauss, 1777 to 1855. Okay, students, here's your chance to, in your own words, define repeated solution. That was nice. We have to go back to that in the video. Example 1, find a number of solutions or zeros. How many solutions does this have? Because x to the third, 5x squared plus 4x plus 20 equals 0 is a polynomial equation of the third degree. Here's our third degree there. It has 3 solutions. They are -5, -2i, and 2i. Finding numbers solutions are zeros. We have another one here, a quartic function here. It is a polynomial function. It has 4 zeros because it has a 4th degree. Here, the zeros are -1, 3, 3, and 3 through our factoring out here of -27 and +1. How many solutions does this equation here have? And students, this is yours. You're responsible for this. Let's see what this comes up with here. 4 solutions, 4th degree polynomial. Example 2, find the zeros of this thing right here, this polynomial. So it's a 5th degree polynomial. It has 5 zeros, and then we use the rational zero theorem to come up with these solutions here by testing them by using synthetic division, or by graphing it would be another way to test it. Using synthetic division, you can determine that -1 is a 0 repeated twice, and 2 is also a 0. So these, by using synthetic division, you discover that. Or you could use graphing too as well. Writing it in factor form, so factoring that, you come up with this here, x plus 1, x minus 2. This is squared, then you have this quadratic here, x squared minus 4x plus 7. Find the complex zeros of f. So this here will have imaginary solutions to it, and they are here. The zeros of f are this array right here, which is a fairly extensive situation here. I mean, you could find these by using the quadratic formula with these plugins here. Okay, find all the zeros of the polynomial function of that. Find all the zeros of the polynomial function. So here is our polynomial. We come up with the 1, 3, and 9 from this here, from our constant. And then we're gonna check now, and we come up 1, 6, and 9. And then this is the graph of that too. So right here at -1 is one of the solutions. And let's see, x plus 1, x plus 3 squared. So -3 is why there's 2 solutions at -3. So the zeros are -3, -3, and -1. So usually when you have 2 solutions at a place on the x-axis is when the graph will come up, touch it, and then go back up through again at -1. That's when you have 2 solutions at -3. Okay, behavior near zeros. Behavior near zero. So example, this here, -1, 0. The graph of f in example 2 shown it's right. Note that the only real zeros appear as x-intercepts. Also note that the graph is tangent to the x-axis at the repeated 0, x equals -1. So this tangency right here that crosses the x-axis at x equals 2 here. This concept can be generalized as when a factor x minus k of a function is raised to an odd power, the graph of f crosses the x-axis at x equals k. So when a factor x minus k of a function f is raised to an odd power, the graph of f crosses the x-axis at x equals k. That's another kind of sub-rule of the zero theorem. When a factor x minus k of a function f is raised to an even power, the graph of its f is a tangent to the x-axis at x equals k. So an even power and odd power, these are the different characteristics of the graph. Thank you very much. That's email me here for more questions or tutoring. Thank you.